Hello, everyone. Good evening, good afternoon, good morning. Really happy to welcome Aaron Spieler today to this Open Neuromorphics talk about a specifically inspired neural model that he worked on. I'm going to bring up Aaron right away on stage.
Hello, everybody.
Hey, man, how's it going? How you doing?
Great. And thank you so much for inviting me and giving this opportunity. I hope I can interest some of you in this work, and I think it's going to be fun. So
yeah. Nice. So your neural model is called ELM Neuron. What does it stand? What does it stand for?
ELM stands for Expressive Leaky Memory Neuron, and it kind of highlights the main differences to other phenomenological neural models, which is that we have these hidden states that I just refer to as leaky memory, which is not a new concept in itself. You might find it in leaky integrated fire models also, where the membrane voltage decays. And the other one that is maybe very different to other models is the expressivity. So we kind of snuck a multi-layer perceptron into a single neural model. And,
nice.
And
sounds very dense.
It's very dense, and this makes it very expressive if you apply a few constraints on the dynamics. And this kind of highlights the recent thoughts that go around the community that maybe single cortical neuron are very expressive integrators, basically integrating their synaptic input over the dendritic tree in a highly nonlinear manner. And we kind of try to combine these two major things into a neural model, and this is what this neural model is about.
Super nice. We're going to hear more about it in a bit. So you have a background. What's your background? Is it in neuroscience? Is it directly in neuromorphic computing?
I mean, I started out in computer science or computational science in Potsdam, and then I did a bit of internship in just deep learning at AWS, and then I moved back, more to say, into my interest of neuroscience, which I already took a couple courses in undergrad, but then I really doubled down on it and computational neuroscience master in Tübingen. Nice. And this is what I've been doing since, working really on computational models of single neurons.
Nice. And you just finished your master, is that right? And
that's
you are now doing an internship at Max Planck Institute.
Yeah, that's correct.
I mean, your internships sound way better than the internships that I've done, honestly.
How did you pull that off? For sure fun. I can only recommend for anyone who is interested, try to hit up PIs at the Max Planck Institute, and they're typically nicely funded, so they might just take you in and give you a nice project. And they do have computer sources, so if you plan on using computer sources, they have some.
Really good. Okay, that's really good. Okay, I will keep that in mind. Thank you very much.
You're welcome.
So with that, I will leave you the stage. Yeah, go ahead, take it away.
Yeah, so again, thank you very much for inviting me. And this talk will be on the expressive leaky memory neuron. An efficient and expressive phenomenological neural model can solve long horizon tasks. And this is in collaboration with Nassim Rahman, Georg Mathios, Bernhard Schulkopf, and Anna Levina, without all of whom this would not have been possible. So I'm super thankful to them. And I'm also happy to share that the work on the ELM neuron got accepted to iClear 2024. So if you're around there, you can come by the poster and we can have a chat if you have questions later. And also there's a accompanying GitHub to the project at my GitHub /ELM Neuron. So just to contextualize the project, basically, it's primarily about modeling cortical pyramidal neuron. And on the right-hand side here, you see maybe a staining of a pyramidal neuron. And they're quite special neurons and quite interesting for a couple of reasons. First of all, they have a pyramidal somata shape. They're very huge. They integrate input presumably highly nonlinearly over their dendritic tree. They have thousands of synapses, and they have projections going far away out of the cortex, which is where you typically find them in the layer 5 neocortex of the neocortex in mammals. And this is basically where our project starts, the modeling, because what we did is think about the high-level computational components that a neuron might comprise, or what the high-level computations might be that go on in a neuron. I will explain that in more detail later. So we have some hypotheses, like how the neuron computes. Then we formalize them a bit more in this typical deep learning kind of way, which is then itself the ELM neuron, which we then evaluated on a very high fidelity data set of input-output recordings from detailed biophysical models of cortical neuron. I will talk about this also in the next slide. And through this, we try to validate our model. And once we validated it, we try to ablate components of this neural model to gain insights about what the necessary components maybe are, how their impact is on performance. And we also do some benchmarks. One of the neuromorphic benchmarks would be the Spiking Heidelberg Digits, where we also introduce a variation of it, which is the Spiking Heidelberg Digits adding, which just concatenates two digits and is temporarily very challenging and compared to maybe other neuromorphic benchmarks. And then we have the long range arena, which is a very challenging machine learning benchmark for long horizon predictions. And through these benchmarks, we also try to chip off some machine learning insights. And because this is a neuromorphic community, I also, this is my favorite part maybe about the whole thing, the engineering part. So I also put in a lot of engineering aspects and how to engineer for long sequences. Yeah, and then as a follow-up, at some point, I would like to, of course, integrate the single neural model into a network, maybe a spiking neural network, which would be the next project, actually. And as a background, maybe one thing that I'm going to just briefly and roughly sketch here is we're utilizing two types of neural models in this project. Biophysical models and phenomenological neural models, latter which is also our model, belongs to this category. So biophysical models are neural models, are models that try to recreate the how neurons compute. So their elements are their computing elements are all in very direct analogy to how the neuron computes. So you typically see such circuits, and the circuits are connected to each other. And they're not, in mathematics, this would be like coupled differential equations. So these models are good at giving mechanistic insight of how a neuron computes. And they give you, so the newest models of cortical layer 5 pyramidal neurons are pretty accurate for showing phenomena that computational phenomena that happen also in biological neurons, and their input-output is quite accurate. However, they're extremely expensive to simulate and compute because you need to solve these coupled differential equations numerically. This is very expensive. And at the end, it's very hard to get a high-level insight into overall what is, for example, this biophysical neuron trying to solve. And on the other hand, you have the phenomenological neural models, which don't give you this mechanistic insight at the lower level component level, and therefore also give you kind of, in comparison, inaccurate input-output transformation. So input would be spikes, output would be also spikes, for example. However, they're super compute efficient. That's what they're made for, essentially. And you can get some higher level insights into the computations, or at least that's what you model. For example, if you look at the right-hand top side image, you might be reminded of a leaky integrated fire model, and some higher level computations that go on in this neuron is it sums its input, is recurrent, and spikes as a consequence of the rectified membrane voltage. So this is kind of high level terms, which you would have to first analyze a biophysical model to kind of gain this insight. And we kind of try to derive high-level insights about the neuron computations in this work by efficiently and accurately fitting a surrogate model to biophysical models' I/O relationship. So we try to leverage the advantages of both models. On the one hand, the accuracy of the biophysical models we leverage, but using a phenomenological neuron where we get the computational speed and benefits. So this would be the structure of the presentation. I'm going to talk about the problem of fitting surrogate neuron models. Then I'm going to talk about the ELM neuron model. And then I'm going to talk about some computational neuroscience insight and some deep learning insights. And I'm going to finish up with a discussion and possibly give you an overview of the GitHub, how you can utilize this for your projects, for example. Okay, so the problem of fitting surrogate neuron models. So on the left hand, you see a kind of a schematic visualization of a biophysical neuron model. And on the left-hand side, you have the input spikes. This can be hundreds or thousands of inputs for the specific data set that we use that was introduced by Benyagev et al. 2021. It had around 1,300 input channels and a single output channel, and where the spikes are recorded and the membrane voltage is recorded. So this comprises a typical supervised learning problem where you just try to fit, given an input, some output. And here in particular, you try to fit your favorite surrogate model to this input-output transformation. So the ground truth is how this biophysical model transforms the incoming spike trains that have a temporal structure to them. This temporal structure is kind of bio-inspired. So let's say you have like 1,300 input channels with spikes arriving, and they get transformed and integrated over this biophysical model, whole dendritic tree, and results in a spike. And you try to capture this with your surrogate model. And so what we did, or what Benyagev et al. Did, is they did it with a temporal convolutional neural network. This can be a black box model, so this can be anything. And we did this using an LSTM, and later on introduced our ELM neuron and the variant of it. The training itself is a vanilla backpropagation through time, and then you have binary cross entropy for the spike prediction. So at every time, you try to predict what is the probability of a spike, an output spike, and for the voltage, you just do a mean squared error loss. And this data set is was generated using a very high fidelity I/O, or it comprises high fidelity input-output recordings from a very detailed layer 5 cortical pyramidal biophysical neuron model. So this is where the biophysical neuron comes in. And high fidelity means that lots of input channels, high temporal resolution, like 1 millisecond. And this is kind of also what sets this data set apart from other data sets that might use coarser grain temporal structure. So maybe they look at like some firing rates, or they just use part of the dendrite. Because again, to generate this data is super expensive. And if you do this task well, so if you fit a surrogate model that is good, you should see something like on the right-hand side, where we have a plot showing kind of predictions and ground truth. X-axis is time, y-axis is membrane voltage. And what you see, for example, for target spikes, over 6 seconds here, we have 5 target spikes. And we have the predicted spike probability, in this case by our neural model. And around spike times, the probability spikes, which means the model is very confident at exactly the right time that there is a ground truth spike happening. And in terms of the predicted voltage and target voltage, they're basically overlapping. And so the idea here is that many models can get a really good fit here. So you could use a transformer, LSTM, temporal convolutional. You can use many machine learning models. They should be able to fit this very well if you give them sufficient compute. But what is difficult, what is actually very difficult, is to do this with as few compute as possible, right? So this is kind of the challenge. And the idea is the better the surrogate model, inductive biases align with the biophysical neurons computation, with its high-level computations, the more compute efficient surrogate model fitting should be. So if your inductive bias is aligned, this is a typical machine learning idea, the easier it is for you to fit the specific data. If your inductive biases are misaligned, it might be more expensive, and in the worst case, not possible. But typically, many machine learning models are able to perform in this task. And in particular, and now I try to show you the results to kind of motivate you why you should care about our model, are shown here, where we compare to the original study that evaluated on this benchmark using temporal convolutional neural network, but we also provide an LSTM baseline and two versions of our model. On the right-hand side, you find the spike prediction. On the left-hand side, you find the voltage prediction. And the x-axis in this case is trainable parameters, but we also have plots showing flops. And the y-axis is AUC, area under the curve, for the spike prediction, and root mean squared error for the voltage prediction. For the spike prediction, we also have true positive over false positive rate, which shows kind of a broader variation. But we use this evaluation metric here because the reference paper also evaluated and presented its results in AUC. And what you also need to know about this benchmark maybe is that maybe the specific number is not that meaningful here. Beyond that, maybe this paper suggested that above 0.991 AUC, the models seem to be sufficiently good for the purposes that they intended the surrogate model for. But it's more about how efficiently you can do this, right? So many models get if you look at spike predictions, kind of the top performance, but where the models really differ is at how much compute they require. And the x-axis scale in this case is log. So what you can see here is that the original paper required 10 million parameters. And then if you think of neurons and how they're typically defined in computational neuroscience, so like these differential equations, you might think, okay, like a recurrent neural network makes sense because there's a lot of recurrent computations going on. So we tested an LSTM. Okay, this already improved an order of magnitude. And then we kind of started to think really specifically, like, what is the minimal components that we think might be needed to match this input-output dynamics as efficiently as possible. And this is where our model comes in, the ELM Neuron, which is in dark blue, and its version branch ELM, which is this brighter blue. But really, these models are, one is a specific hyperparameter setting of the other. And these in total give another order of magnitude improvement. So in total, you have here around 3 orders of magnitude improvement, getting the same, so to say, performance, but at 3 orders of magnitude less compute, which is huge, especially if you consider that, for example, this TCN network, its inference cost is already itself 3 orders of magnitudes cheaper than a biophysical model generating this the same sequence, so to say. So this is a huge improvement, and yeah, the performance saturates at some point because there's some residual uncertainty just based on the data set. The dynamics are very complicated. There is information getting lost, kind of, and it's might be close to a chaotic system, essentially, especially around spike time. So kind of the data set caps out at some performance, but how efficient you can make them is really the key. And in the end, we got models which only have 10,000 parameters, which is especially impressive considering the input dimensionality on this problem is 1,300, essentially. And then we see the similar pattern on voltage prediction, but all of our models performed a bit better than the comparison model. Okay, if there are no questions, I would move on here. Now to the expressive leaky memory neuron itself. This is a sketch that basically summarizes our hypothesis about what are the necessary high-level components in a pyramidal neuron's dynamics. So we see here a cortical pyramidal neuron with its dendrites. And the idea is that such a cortical neuron receives its input through these synapses, which are marked in green, and highly nonlinearly, potentially highly nonlinearly, integrates them over its dendritic tree, which can be very sophisticated, as I mentioned, and maybe integrates this into intermediary values or multiple hidden states that change over time. We call these memory values in the end, but in the end, it's just some hidden state that needs to be tracked over time. But it could be 1, it could be 10, it could be anything really. You don't know a priori. Evidence suggests that it's probably more than 1 or 2. And then at the end, there is some output generated. And about the architecture itself, I'm just going to talk about the rough architecture and then go into more and more detail. So basically, there are 4 components which reflect these ideas about a cortical neuron. There's the current synapse dynamics, which is in green, the leaky memory dynamics, which is in blue, and the integration mechanism dynamics is in this orange, and the output generation dynamics in this pink purple. And this model has its input at the bottom. So xt is the input and yt would be the output. And what's important to note here that because this is a phenomenological neuron, so we moved away from the biophysical model because we want to abstract this, so to say, implementation details of a neuron, and we want to kind of capture the high-level ideas. These components only represent kind of analogies. So it's not a one-to-one mapping. You lose this. This is just how we think about these components and reason about them. Okay, so if you would have a single this computational graph here really displays what our neural model is doing in one single time step. So at a single time step, it's getting a high dimensional input xt, and it's transforming it through its components and generates one output yt. And okay, on the left here you see the hidden states m before and mt, so after the computation. So as it's a recurrent model, it gets its own output fed back. Here for the memory values and here for the synaptic values. So this is the hidden state s after. And so to say, if you imagine this neuron processing a sequence of inputs, you would have to imagine this model copy-paste multiple times after each other. So this is maybe xt minus 1, this is xt, this is xt plus 1. And this is recurrently integrating its input through its synapses and its hidden states, which are both. So the hidden states and the synapses, which are also hidden state, get fed into this multi-layer perceptron, which then generates an update to the memory states. What's important to note here maybe is that m is a vector, and so is s. st has the dimensionality of your input. So if you have 1,300 input channels, which is not an unreasonable large number for a cortical neuron. Many people say up to 10,000, for example. And m is also a vector on the order maybe of 10 to 100 typically that you could initialize this model with. And this also comprises one of the major differences to many other phenomenological neuron models, where you a priori have 1 or 2 hidden states. So if you think of a leaky integrated fire model, m would be the membrane voltage, and you would have just a single float value. Or for the adaptive leaky integrated fire model, you would have 2. The membrane voltage and the adaptive threshold. Here, this is a hyperparameter, and you can just set it yourself. So this kind of is a parameter that you need to ablate. And actually, this is also, we suggest, maybe the only parameter that you really need to ablate. The other ones can be set based on the data set and based on this value, the dimensionality of this value. Yes, okay, what else? The inputs are processed in discrete time in this model, as in typical deep learning fashion. And one important detail maybe to note is that xt can and does immediately influence the output yt. So this is not always the case in dynamical systems and in recurrent models, but here it's definitely the case that immediately xt can influence yt. So the signal propagates fast forward. And here is I go a bit more into the detail and also just again rehash basically where the naming is coming from. So we have this vector of hidden state that is the leaky memory. Why is it leaky? So memory it is because it's the hidden state and it lets the neuron remember things. And it's leaky because we define a decay constant for each memory value itself. So there's as many, this has the same dimensionalities as MT. But it's leaking because this is a constant between 0 and 1. So at every time step, it kind of erases from the memory. And it's decaying over time. And this can be also seen as leaking away. And this is also, for example, where the leaky integrate and fire model gets its name, where the membrane voltage is kind of leaking out of the neuron. Here we apply the same principle, but just to a vector or a hidden state with a configurable dimensionality. And expressive is where the model is getting its second part of the name, where the MLP is kind of integrating its both its memory input or its hidden state and the synaptic trace at each time step in possibly a highly nonlinear way. And the analogy here would be, again, the dendritic tree, the intricate dendritic tree of the cortical neuron and all the dynamics that go on at these synapses, possibly also within the dendrites. So this can be tuned, so to say, on your individual needs. So most of the phenomenological neurons that I know of a priori set this to linear integration. However, then you don't even have the chance, so to say, to evaluate, wait, maybe in my case, a kind of nonlinear integration or highly nonlinear integration makes more sense. With our model, you can do this. You can set the MLP hyperparameters to go from linear integration to highly nonlinear integration. So this kind of represents a family of hypotheses about how nonlinear is the integration. Then you can think of S as just a synaptic trace. It's just the typical current synapse dynamics that you would find in computational neuroscience. But what this means is basically it's a low-pass filtered trace of the weighted inputs. These are the weighted inputs with the WS. And this would represent something like an IPSC or EPSC. But if you don't know these things, it's like basically think of the spike as being 0 or 1. So 0 being no spike, 1 being spike. And at each time step, there might be a spike, so a 1. And then this 1 decays over time back to 0, which depends on this time scale. Also here, important to mention, tau m is also a vector. And the longer the time scale, so these tau m can be from close to 0 to very large, let's say 1,000 milliseconds. The larger you have this time scale here, the slower your memory is decaying. So 1,000 would be very slowly decaying. In fact, over 1,000 time steps, it would decay to 1 divided by E of its initial value. So if a memory MT is 1 and the time scale is 1,000 milliseconds, after 1,000 milliseconds, it would be 1 over E. But if it's a very fast time scale, then it would immediately basically go to 0. So there is a question, the ELM tends to forget over time. Is ELM able to solve this issue? Also, this is related to spiking neuron. What are the current limitations regarding this? Exactly, these are going to be the benchmarks basically later that we going to look at. The long-range arena and a version of the Spiking Heidelberg Digits that is very temporally demanding, where we're going to evaluate this. And yes, this neural model is able to solve very challenging temporal long horizon task. Hence, also the title of the paper. We're going to look at these benchmarks very soon. Yeah, but actually, yeah. Okay, let's just leave it at that. And then there's a linear readout, which doesn't add to the complexity. And this part, for now, you only need to know that these three components together make the dynamic stable, and in particular, limit m. So m is a vector that, of float values, but these float values can only vary between minus lambda and lambda, so within a certain corridor, depending on lambda, basically, and if tanh is between -1 and 1. So if it's between -1 and 1, this can vary between minus lambda and lambda. And this is for stability reasons only for now. And then there's the branch ELM version of our model. And what you need to know about this is that it's basically the same as before, but we introduce a component called branch sum in between the MLP layer and the synaptic trace layer. And the idea here is that, okay, you look at the dendritic tree, but as you can see, not everything influences everything immediately. So if you look at the figure on the left, like the schematic, then this bright blue is like the dendrites. And a dendrite at the very top is not directly connected to the dendrite at the very bottom. So it's kind of a hierarchical integration where not everything is connected to everything immediately. And in particular, it is believed that neuron branches are believed to compute rectified sums of their input. So a rectified sum is, of course, super easy to compute because it's non-parametric, doesn't require any additional parameters, and is just a summation, right? So if this is true, and we can exploit this, we should be able to drastically reduce the required compute and also the number of parameters. This was introduced basically because we noticed that most of the parameters in compute are going into the MLP. As I said, the benchmark dataset, the Neuron IO, has an input dimensionality of 1,300. So this means in the next step, there is a matrix of size 1,300 times the hidden size of the MLP. So for example, 50. So 1,300 times 50, which is huge. And yeah, so we managed to exploit this, and we do compute now rectified sums in these sums first in the branch sum. How we do this, you take this one, for example, 1,000 dimensional input, you slice it into branches or cut it into branches, and then you take this branch, so these are the activations, and you just sum it. So for example, in this example here below, you kind of have the dimensionality of the input to the MLP. Again, there is like a bit of input also from the memory units, but it's negligible in terms of dimensionality compared to the input. And we kind of have an example up and running, or in the benchmark we show where the branches have a size. So this here it's 2, but we use 100, yeah, and we have 45 of these branches, which means that in the end we reduce the input dimensionality of the MLP from the input directly from, let's say, 1,278 to only 45, which is of course huge, and this has an impact on the flops required and the parameters required. And I said rectified sums, so the rectification we let the MLP handle in a parametric way. And so here, before I move on to the benchmarks, I just want to kind of show you a summary slide of this experiment, which is kind of also the most beautiful plot to me of the whole project. And actually, you can also recreate this figure in the GitHub that is hopefully shared already by now with you. So what we see here in panel A is you have on the y-axis the number of input channel, and on the x-axis you have like 2,000 time step. And keep in mind, the model is trained on 500 millisecond long sequences. So, and to me, yeah, blue is like inhibitory input, red is excitatory input. So each dot is like a -1 or a 1 that is fed at a very specific time step into the neural model and is then integrated into its output. And this basically looks to me like noise, essentially. But using enough training data, you can actually predict the very specific membrane voltage or target voltage and the output spikes, which are incredibly sparse. So there's like 3 target spikes on 2,000 time steps. So it's like 3 out of 2,000 are 1 and the rest is 0. You can very accurately predict this. As a bonus, you get some really nice visualization of the synaptic traces, as you would find maybe in other models. But then also you get a very beautiful visualization of the memory units, which display different temporal characteristics. So either very fast or very slow temporal characteristics, which is kind of defined by the time scale of the memory unit. And you can do this with only around 8,000 parameters. Whereas before it took 10 million, now it takes below 10,000. And you get the same accuracy. And this is only possible because basically the way the components or the high-level computations in these components that we propose in the ELM neuron match really well with the biophysical model. And this is a huge reduction, and it results in a very neat little neural model, essentially, that also has some really interesting dimensions along which you can ablate it. Yeah, and if you're interested more not in AUC, but true positives over false positives, I also included a plot here in the top right, where you see that the differences between models vary a lot also. And this is in the end what you care about, right? You want to very specifically predict when it's spiking. And this is kind of the visual summary of this. And now to the computational neuroscience insight. So this section is kind of about what are the components, the high-level computational components in cortical neurons maybe, and which component matters for what. And then we're going to take about the deep learning aspect, which is about the long-range prediction and so on. So what does it take to efficiently learn a biophysical neuron's I/O? We propose that it takes around a dozen memory-like hidden states, highly nonlinear synaptic integration, some longer memory timescales on the order of 50 milliseconds, and around 5 to 10 times faster input than forget timescales. And this slide kind of summarizes this. And these are also the dimensions along which we propose you could get neuroscience insight by ablating the model. So in the way we showed, so you fit your model to a biophysical model or another neural model's data, and then you kind of do these ablations. And so the base model, which is marked by the triangle, is this model which I showed before, how it performed. And now we kind of ablate these components very specifically without changing the rest. And so, for example, in terms of memory units, so hidden state size, we see that between 10 and 20, that's when it starts to flatten out. So this is why we say around a dozen memory-like hidden units. What we see is, for example, many phenomenological neural models use linear integration. You can do this with our neural models as well, but you will get just very bad performance. And even if you give it a hidden layer, this is already a very significant improvement in performance, but only once you go, for example, for a hidden layer dimensionality around 40, which is in this case twice the number of memory units, then you get the performance leveling out. And interestingly, you don't gain by having more, a lot. Then I would like to focus on the timescales, where we kind of ablated the maximal timescales, the minimal timescales, and also what if you make all timescales the same. And what we find here is that basically you gain a lot by giving the model longer timescales, in this case up to 50 milliseconds. And the model really doesn't like small timescales if you only have timescales, right? Like, for example, maximal 5 would mean that the model got timescales between 1 and 5 milliseconds. For constant, it's kind of the same pattern, and for minimal, you only gain a little by not giving it very small timescales. Although, to be fair, in our model, the way the memory update works is itself a kind of fast memory timescale. So the model can kind of compensate for not having very fast timescales. So maybe this only reflects this phenomenon. And then lastly, which I'm not going to explain in too much detail, but essentially this lambda parameter controls how much, how the input timescale compares to the forget timescale. So 10 would mean that the input timescale is around 10 times faster than the forget timescale. So to remember things over long timescales, you need long timescales. However, for each timescale, you also have an associated kind of input timescale. So how fast is information absorbed? And 10 means that it's 10 times faster absorbed than it's forgotten. And if you think about this, this really, to me at least, intuitively makes sense, because you don't want, if I tell you I'm going to the movies tonight, you want to kind of remember this maybe at least 10 times as long in your short-term memory as I need to tell you that I'm going to the movies, right? So you don't want to repeat this 10 times just to be able to remember it, for example, for 10 seconds. And actually, I just updated the GitHub with a kind of a version 2 implementation of our ELM neuron model, which takes this idea very literally. Here in this current model, it's kind of a derived quantity, the input timescale, how fast it is. But if you take this notion very literally, then you can also get, interestingly, rid of some of the instabilities. So there are some, as you can see, maybe it's overlaid, but if you have a lot of very fast timescales in the model, this could be because you make all of the timescales very fast, or you have like a ton of timescales. You have 150 memory units, then a lot of timescales will also be fast because they're initialized kind of lin space or log space equally distant. Then you run into these instabilities, but it seems like we got rid of them with this version 2 implementation. And also you got rid of the instabilities here. So basically this is just monotonically increasing, and this is still decreasing just as like, but for example, these ones represent runs that errored out, and now we don't get these, it seems like, in preliminary experiments. And then now we start talking about temporal processing, in this case, a bio-inspired talk and also a neuromorphic benchmark. I'm just watching time. So you might know of the Spiking Heidelberg Digits. So for example, if I say 8, then this has a temporal structure. It's basically a spectrogram or where of the digit 8. So if you have a time on the x-axis and maybe frequency on the y, then maybe if you looked at the spectrogram of me saying 8, this is how you would look like if you encoded, for example, with spikes. And maybe the spike frequency would correspond to the kind of power of, or the intensity of the frequency at that frequency. And so there's the Spiking Heidelberg digits where it's just these digits, and you need to classify which digit is it. And however, it turns out that the temporal structure of this data set is not as demanding as could be. And we kind of created this very simple modification of the data set where you take 2 of these digits, you concatenate them, and then you try to predict their sum. So 8 and 1 would be 9. So this is like a 19-class classification problem. And what's interesting about this, now you kind of cannot cheat this data set by just kind of extracting local features and making your prediction on this on that basis. So you still need to identify the digit based on local features, but you have to remember it until at least the second digit when you combine this knowledge with the current digit, and then to finally make your predictions. And also, important note, we suggest that all models that compare against us, and also how we did it, is that there is a last time step loss. So the model that train on this really just get an error signal at the very end. And this task might be neuro-inspired, or I would like to argue that it is like this, because there's some papers showing that maybe neurons, single cortical neuron, might be able to do some simple arithmetic, like for example identifying digits or like adding digits. And this is kind of what this data set represents. And it's the inputs are 0 or 1, and then there are 700 inputs at every time step, and the spikes are very sparse in space and time. And this kind of reflects the ideal conditions also for the ELM neuron, which works very well on space-time sparse data. And here we have a comparison against an LSTM and a spiking neural network, and then we have chance. And we also have a parameter on this data set, which is bin size. So essentially, a bin size of 2 means that within 2 milliseconds, all spikes are kind of aggregated. And 100 means that over 100 milliseconds, all spikes are integrated. So there's an interesting dynamic going on there. So the higher the bin size, the easier the temporal problem is, but the more kind of temporal detail you also lose, so you might not be able to solve the data set as well. And this is kind of exactly what we see on the test set. So for example, for the ELM neuron, it gets some performance on bin size 100, but then actually performance goes up for smaller bin size, so for more temporal detail. So the ELM neuron is able to take advantage of more temporal detail if properly initialized, whereas the LSTM kind of just dies. So this is like a vanilla LSTM initialization, and SNN isn't even able to pick up on the signal properly. So we also did the benchmark on Spiking Heidelberg Digits, where the SNN is able to perform decently, and the LSTM kind of matches the ELM performance, which shows that for the default LSTM performance and default, this is a lift-based SNN, they're really bad at temporally integrating over long horizons. And just to give you a sense, so bin size of 2 milliseconds would mean there is 1,000 time bins. And if you then ablate, okay, what makes the model work? Then there's two main components: the complexity of integration in the neuron and the time scale. And what you see that here is that at least 300 millisecond time scale is needed to solve for 2 millisecond bin size. And if you go, and in terms of complexity of the model, around 100 hidden units, memory units, you kind of get the peak performance. And this shows kind of that if cortical neurons are able to do this, we need longer timescales in them than maybe from the previous benchmark is known, which showed 50 milliseconds. So I hypothesize that maybe this is because the data set is generated using a static neuron, so long-term plasticity really doesn't play a role there. So maybe using long-term plasticity and neuron would be able to kind of solve this. And then we go to the deep learning insights. And this is kind of the long-range arena is kind of the benchmark for long-range dependency prediction. And we also use this, of course, because machine learning community cares about this. And for me, it's personally more like, how far can we push the ELM neuron? And we can push it far, and it performs decently on even a task which have a temporal context length of 16,000. Which would be Pathfinder-X. It can solve those, but it doesn't get SOTA, which maybe should not be surprising, as it's a pretty simple neural model, or it's a simple architecture, maybe a very complex neural model, but still simple architecture. But this might be kind of alleviated if you move to assemblies of ELM neurons, right? So you typically wouldn't try to solve like very complicated tasks using a single neuron, but maybe an ensemble of single neuron. And we also very fairly compared against a Chrono-LSTM, which is kind of an LSTM variant where you take the idea of you need long time scales to solve long horizon problems very literally, and they derive like analytically an initialization for the LSTM, and then the LSTM performs much better than previously, but still fails, for example, in Pathfinder-X, and also in general, it does not perform as well, but quite close. But also one thing one should mention is that this data set benchmark is kind of very, in one sense, adversarial to the ELM neuron. So as I mentioned before, the ELM neuron performs maybe well, or is even made to perform well on very sparse data. So large input dimensionality and sparse input spikes also in time. However, this benchmark, like all of these examples, are flattened out 2D things. So at each time point, you get a float input, which you first need to kind of convert into categorical value for the ELM neuron. So the input dimensionality is very small. This is why both ELM neuron and LSTM get around the same number of parameters in this. So yeah, you probably, the ELM neuron is not made for this benchmark, and you probably wouldn't want to use it where you have a very low input dimensionality. And this is a very interesting slide that I added specifically for the neuromorphic talk, where I just kind of ramble on what I think are the engineering takeaways for RNNs for long horizon prediction, for learning complex dependencies over long horizons. And there are basically three components that I think are necessary. So for learning long range dependencies, you kind of need to solve the vanishing gradient problem and the exploding gradient problem. The vanishing gradient problem we solve here through the use of explicit timescales, right? Like long timescales, long temporal integration, and kappa m, which leads to a controlled but slow decay. And in order to solve the exploding gradients problem, we use this construction here, the tonnage, the 1 minus kappa m, and the lambda to get a controlled but also bounded growth. So in one case, you want slow decay, and in the other one, you want bounded growth. And these two components, as far as I can see, solve the vanishing gradient and exploding gradient problem. And in fact, I hypothesize that maybe all successful architectures need to make use of this, either through initialization, like we saw in the Chrono-LSTM, or constraints or components. Then the second part is, how do you learn complex dependencies? I hypothesize this is kind of orthogonal. You can learn very simple long-range dependencies if with a certain architecture, but you need another component for learning complex dependencies. And this is not new. This is just basically the story of deep learning. You need to apply successive nonlinear transformations. We do this through the MLP, so we put the nonlinearity in the recurrence to get a highly nonlinear processing. Alternatively, you can apply also nonlinearities through successive layers, so like by stacking layers on top of each other. And this is kind of what Orvieto et al. Showed in 2023. So you can have very simple recurrence, linear recurrence, but by stacking layers on top of each other, you can solve very long horizon tasks very performantly. We do this differently, but this is kind of an alternative. But in both cases, you need highly nonlinear processing. Okay, and then you might ask, okay, but what about X, this component, that component, whatever? So I think what's hurting is things that go against one or multiple of these three principles. So either, for example, you have parametric input-output gating, you have parametric time-varying timescales, you have excessive and uncontrolled amplifications, or you have few and simple nonlinearities. All of these hurt one of these principles, and then you will get either no long-range dependencies solved, or you won't get complex dependencies solved. And all the rest is kind of neutral. So you can think of this maybe like a three-dimensional space, controlled decay, controlled growth, nonlinear processing. And if your model covers these three dimensions, you're good. But you kind of also need to make sure that you're not hurting it in any way. And what makes the ELM neuron unique and with respect to these principles is that it packs all of these requirements into one module. And this is possible through the nonlinearity in the recurrence. So some people before this paper believed, oh, we cannot solve very long range, like 16,000 length long range dependencies using RNNs because there is such a nonlinearity going on. And we kind of showed this is not the case. Solving long-range dependencies is about a different problem. And if you make sure your dynamic is nice, you can solve a very long-range problems also with a highly nonlinear recurrence. And then you might ask, okay, so we have the MLP covered, we have the M covered, we have this covered, and okay, linear readout. But what about these? What about the branch sum? What about the synapses? Traces. And there I would say the branch sum and the synapse decay compensate for very space and time sparse data. So if you don't have very large input dimensionality, then you probably don't need branch sum and also sparse input dimensionality. And if you don't have very sparse time input, then you probably also don't know the synaptic trace. So for example, here we need longer timescales for solving Pathfinder-X, and the branch sum is instrumental in kind of efficiently solving the neuron IO task. And for example, in the Spiking Heidelberg Digits, I showed you a couple models, and the branch sum is much smaller than, for example, the vanilla ELM neuron. So this is about, so we have the three components that solve vanishing, exploding, and nonlinearity. And then we have two components that solve sparse in time dimension, sparse in space dimension. And this is just a brief slide. So I think inductive biases are not dead. So if your inductive biases are aligned very well with your task and data, you can drastically reduce compute cost. And bioinspiration can still serve as a powerful source of novel architectural design. And my last 3 or 4 slides I want to talk about the limitations to be very transparent. So the results are using backpropagation through time. And for example, on the Spiking Heidelberg Digit and long-range arena, the ELM neuron models are bigger than are necessary for good results on the neuron IO task. So don't take this as an example of how neurons learn. Then the recovered ELM neuron hyperparameters like number of memory units, time scales, stuff like this, MLP nonlinearity, it depends on your definition of good fit. So from the previous paper, we had one definition, but depending on what you want to use your ELM for, or on what you want to use the pre-trained models for, you might need to choose a different model with a different size. Then the dendritic structure so far is very basic, but we're working on this. And there's limited mechanistic insight. As I said, this is a phenomenological neuron model. So here we are lacking identifiable locality and identity. So you're not going to be able to map like, oh, this is something in a biological neuron, and this exactly is this in an ELM neuron. We kind of abstracted a lot of the biological details away to get this improvement in computational efficiency. And yeah, there's two things I already mentioned, but the synapse dynamics and branching are only going to be useful if you get space-time, very sparse data. And here's a very opinionated, quick take on maybe, okay, you're wondering, okay, but then when should or why should I use the ELM neuron? So compared to, for example, long short-term memory and like other recurrent neural networks, we offered the possibility of getting some neural insights. This is, I showed for the neuron AI dataset an example of how to do this. We're more compute efficient, especially on large dimensional and sparse input. We have these explicit timescales and stable dynamics, so it kind of solves these problems of vanishing and exploding gradients, especially the version 2, I think, of version 2 ELM neuron. And we get a wide range of size and expressivity. So you can make unlike the LSTM, you can make the ELM neuron very, very small for even a very large input dimensionality. And you can really you get a fine-grained control. Where do I want to give the model more power? Is it more, does it need to remember more? Do I give it more memory units? Does it need to process more non-linearly, more complex relationships? Okay, I give it more non-linearity, etc. And we have a very simple architecture, like no parametric gating going on and so on. But it's also less powerful than state-of-the-art models, less versatile. Again, float input, you need to think about how to feed this in a sensible way. And it's less parallelizable, so because of the nonlinear recurrence. But to me, especially the right-hand side is interesting because you want to, of course, compare it maybe to leaky integrated fire model and other phenomenological neuron models. And here, I think there are really some very powerful benefits that if you need them, might be one of the few models that can give you this, where we have learnable neuron dynamics, variable hidden state size, modifiable timescales and diversity, configurable input integration expressivity, and very stable dynamics. Also, essentially because we don't have an explicit reset, which, by the way, biophysical neurons and biological neurons also don't have. This is a kind of an observation, which is hard-coded in, for example, leaky integrated fire neuron. But you lose some interpretability of the components, right? Like what is an MLP and a neuron, and less interpretable dynamics, especially at initialization. And then for the current and future directions, so currently we have working on an enhanced ELM with stability at the hyperparameter extremes. This is what I was talking about, where if you have a lot of very fast memory timescales, this can be unstable. But I think I just pushed the version 2 of the model. In preliminary tests, this gets kind of rid of those instabilities. Then we're testing fit to other biophysical neuron models. We try to relate the complexity of the model to the dendritic structure of the model that is being fit. We have we try to find out what are the high-level computations in a single dendritic branch. So dive deeper into what is a single dendritic branch computing. And yeah, you could inspect memory weights and timescales, but this is the kind of then the really interesting part to me in the future. I want to kind of look at, okay, how is the expressivity of a single neuron influencing the expressivity of the whole spiking neural network? Using our ELM neuron, we can ablate the expressivity and individual components like few other models essentially. And we can also then look into the connectivity, look into which parameters are maybe shared, trainable, like plasticity essentially, and explore initialization and regularization in a network with very sophisticated single neuron components. And then evaluate it maybe on very challenging language modeling tasks also. And at the cherry on top would be if one is able to do it using space-time local learning rules. And yeah, there is the last slide of this presentation, essentially, where I want to leave you with an argument for spiking neural networks on conventional hardware. So I often hear the argument for efficiency in terms of energy efficiency, but I think there is an argument that is not, I don't hear it often or at all maybe, but I think it's true. So if you look at the DRAM and the interconnect bandwidth growth over the last decades and compare it to how the number of compute grows, then you get a plot like this, which I basically stole from this Medium article. But essentially, you also get the same for the memory size. So this would be also similar to kind of the bandwidth, like it's very shallow growth or slow growth compared to flops. And now, if you think about, okay, what would be the ideal model architecture that is able to, and training algorithms that are able to utilize this gap in growth speeds? Well, it would have to be one that leverages a lot of compute locally during inference in like kind of localized modules. Again, you want to prevent communication a lot. It would have to be sample efficient, local and online learning. Again, because you don't want to communicate a lot. You want to compute as much as possible locally. And again, this is kind of the space and time local computation. And then you want to communicate very sparsely, essentially, with highly informative messages, right? Because if you can do this, you really don't need a lot of bandwidth. If you have very sparse messages that are highly informative, this is the between modules. And then, I mean, the cherry on top would be if it's straightforward to scale this architecture, so this module composition. And I think basically this is what the brain does. And so I believe the neuroscience evidence points in this general direction, because what I basically describe is the brain in some sense, with neurons as the modules of computation. And for me, the ELM SNN would be one attempt to move into this direction, where the question is, what size ELM neuron will, at one point, will it give you diminishing returns in terms of the overall computational power, right? So how much compute during inference and for your kind of computing and solving your task can you move very locally into a module, for example, a very complex single neuron that communicates using very sparse but highly informative messages. And I think this, even if it's not the ELM neuron or anything like this, in principle, in my mind so far, this is kind of inevitable, but because the flops are growing so fast, but the bandwidth so low, at the communication is basically the bottleneck. So you want to do a lot of local stuff. Yeah, and there is a GitHub where you can look at, although I implemented in JAX for readability, I re-implemented it in PyTorch. Also, there's like Torch SNN. So I believe the community is more familiar with PyTorch. And yeah, we also have data loaders for Spiking Heidelberg Digits and the Spiking Heidelberg Digit Adding version, the new dataset we proposed, and also the Neuron AO, where we have also training and evaluation notebooks. And also you have pre-trained ELM neurons, so you can use them as is for your next project. And I heard some people are working also on cool follow-ups using these pre-trained models. And yeah, you can, for example, also generate this image plot, like right from the from the notebook. And yeah, PyTorch implementation is for some reason slower than JAX. I really gave it my best try. I don't know, maybe if there's some PyTorch guru out there, can take a look what I did wrong. But it's about half as slow. Now the version 2, I did some improvements. It's not quite as bad anymore, but yeah. And that's it basically. So thank you for your attention, and leave questions somewhere. I will find a way to answer them, even if we don't find time to answer all of them here.
Thanks so much, Aaron. It was really cool talk. We have a question from Miles Keating.
There's evidence of precise repeating spikes in vivo. You simulate exact spike timing of cortical neurons. What is your opinion on the significant utility of temporal precision and spiking activity? Okay, I see. So this is a super difficult question, and I don't feel very qualified to answer this, because also this is not what the project was about. But what is definitely true is that if you are able to take advantage of very precise spike timing, you can get, in theory, much more powerful computations than if you just look at aggregates. I think this is overall true. So if you can utilize this, whether this is true in neurons and biological neurons or not, to what degree, I think this is not known definitely to date. But what is also true is that cortical neurons, cortical layer 5 pyramidal neuron, like biological neuron, spike very sparsely, like on the order of very few hertz. So essentially, it has to be true to some degree that the very precise timing is necessary, because you don't have that many spikes to work with.
Very, very good. Thank you. There's one more.
ELM neuron formulation can be obtained from basic LIF model. There are very many similarities. In fact, there are so many similarities that you can, essentially, if in the ELM neuron, you take the MLP and make it linearly integrating, and you give the ELM neuron only a single hidden state, so single hidden state and linear integration, you basically have a leaky integrate and fire model with current synapses. And then you have, almost exactly the same number of parameters. It's slightly different because of, for example, in the LIF, you just do a sum, but in the ELM, you would do a sum and have a bias. So stuff like this, but essentially the same number of parameters. And then you get a model that is super similar to a leaky integrated fire model, but is much more stable in its training, essentially, because you don't have this reset, and you have this stabilizing part on how the lambda and the kappa n is integrated. So yes, this was also the intention in the beginning when I was designing it, that you can span a large range. So not just super complicated, but you can make it really very simple, essentially as simple as a LIF. And then in your project, you can tune the different hyperparameters I presented to your needs. So you don't need to make an a priori hypothesis about how complicated neural model do I need. You can use the ELM neuron and find out, which is, as far as I know, not really possible so far. Like, you would have to choose a neuron model, and if you want a more complicated neuron model, more nonlinear integration, well, tough luck. Then you need to change it, take a totally different model. You need to move to ALIF, or you need to move to Hodgkin-Huxley, or you need to move to I don't know what, But here it's within a single neural model, and changing complexities is just as simple as changing one hyperparameter and adding, 2 more memory units, 1 more hidden layer.
Thank you for that. I have a follow-up question for that. So there's lots of neuromorphic projects that try to bring a lot of this complexity into replicating these biophysical models to some level, I guess. How do you, now you basically just learn all these complexities, reduce the parameter count, and simulate it on conventional hardware. What's your take on, do we then need neuromorphic implementations that are anyway very constrained? Do we need a hardware implementation of the ideal ELM neuron? Do you maybe use, you train your ELM neuron to find the best potential one for a specific application, then you cast it into hardware? Maybe.
I don't think you need to go that far. And actually, I was also thinking about kind of neuromorphic implementation of this, although this is, as of right now, not implementable in neuromorphic hardware. But my wish would be that at some points, at least, we get chips where you could do this. But for example, if you think of the memory trace, this is my bad. So if you look at this model, so the memory trace, this should be implementable in hardware, right? This is just this is implementable in hardware. Synaptic trace, also implementable in hardware. Synaptic weights, also implementable in hardware. Linear readout, basically where I think we are not there yet, if I'm correct, is the MLP, basically. The MLP and the WS. But in fact, in initial formulations of how I showed this graph, I didn't even write MLP there, just a phi. This can be a nonlinear function. So as long as it's trainable, kind of, and it's highly nonlinear, I think this should suffice. So you can replace this with your favorite nonlinear function approximating module. So I don't know what there is in hardware because I'm not that deep into that right now. But if you can do this, I think you already moved a lot into this direction. And I believe there are also some chips which allow kind of are Turing complete at the single neuron level, but don't allow for this many. But we're moving really close to it. So for example, the smallest neuron model on the neuron IO task has only 4,000 or 4,500 parameters. So this is not quite there, but very close, way closer than 10 million, for example. And my hope would be that, I mean, if I can make a wish, then this would be, okay, let's just not fixate up, let's just not put it into hardware how exactly the single neuron is computing, and leave a bit more leeway, so to say, on the single neuron level. How complex really is it? Because I feel like not even in software or theoretically do we really know this. So this would be my wish. But I don't think that it needs to look like exactly like the ELM neuron. I think it needs to adhere to these principles, essentially: controlled slow decay, controlled bounded growth, and highly nonlinear processing. Whether you do it like this or other way, I think is not maybe the deciding factor. If you can do these three principles in hardware, then you can do basically anything that you could do with the ELM neuron in hardware. So this would really be cool. Does this?
I really like the idea of learning the complexity. I think that's really cool.
Or at least have it ablatable. Like, don't put into hardware what you don't know that is absolutely true.
Yes. And regardless of like the amount, let's say, the complexity that you encode in your neural model, like you still train it as an RNN, as a recurrent neural network.
Yes.
Like there's now other there's state space models now available. There's transformers can be parallelized over time. Like how do you see like scaling up training ELM neurons or
so at the single neuron level, we run into this problem basically, which is kind of covered by my face, but it says basically that less parallelizable, i.e. nonlinear. So the single neuron is nonlinear. So if you only intend to use a single neuron model and you want the maximal throughput, I think you shouldn't use the ELM neuron. Basically, it comes down to this because it's not parallelizable. Unless you have like a biological application in mind and you need kind of this neural insight. However, also, as I mentioned, I think what is needed is basically a spiking or like a composite model where we take this idea to its end and basically use ELM neurons as neurons in possibly a spiking neural network. And then the beautiful part about this is that individual ELM neurons, then you can take advantage of these scaling laws, because in parallel, you can run 10,000 ELM neurons in parallel. And if you recurrently connect them, then maybe this is enough to solve very complex tasks. If this is enough. So this is an open question, essentially. And my bet would be if I find a good way to, as a community even, it's not just about ELM neuron, but if we find a way to compose modules of computations, let's say neurons, into larger networks, then we can run each neuron in parallel. So I'm talking here about phenomenological neural models, yeah? So you can run 1 million in parallel. It's trivially parallelizable. You take very good use of compute if you don't train them using, for example, backpropagation. So this would require a training algorithm that is also space-time local. But if you have a space-time local training algorithm, and let's say we find that, I don't know, ELM neurons with 5,000 parameters, 10 memory units, and a single hidden layer is kind of the sweet spot between how complicated do we make a single unit of computation, then this should scale much, much better than other algorithms like S4, or I don't want to name specific ones because I haven't tested, but like between any other model that requires basically a layer is computing a matrix multiplication. If your RNN is computing a matrix multiplication, a dense matrix multiplication in a layer, so then I mean the compute grows quadratically, but that's not the problem because we have enough compute. But essentially the memory is required for huge matrix multiplications is so huge, and you need to shard it then across GPUs. Oh, now you're sharding a matrix multiplication across GPUs? Well, good luck. Now you're communicating dense vectors of float values, and this is just causing havoc. And this is why currently, I don't know, I mean, of course, but I suppose that at Google, like, you know, at OpenAI, like all the people who use the biggest of transformers, 70 billion, maybe during training they can justify this size, and somehow they make it work, although painfully. Then they try to quantize it in all sorts of ways to kind of make the models post hoc smaller in terms of also communication, or they make the matrix multiplication sparser. I don't know, there are a bunch of techniques, but basically this is your bottleneck. Like if you have huge matrices, they're densely multiplied, there's just so much communication going on if you need to shard them across GPUs. And this is what's currently killing probably a lot of applications of these super large transformers, I guess. And this is also what's kind of the limit. Even if it's not killing them, this is kind of the limiting factor. I don't think, or although I'm really not an expert in this, I suspect that not the amount of compute is the problem, but the amount of the compute is distributed. And if you need to take advantage currently of architectures, they're just communicating with float values and vectors. And you really, I mean, ideally you communicate very sparsely, and then your architecture is going to scale. And if the ELM or some other neural model, for example, is able to take advantage of this, I mean, then it's going to scale much better. But if you mean with scaling that it's also going to perform, well, this is to be seen, right? It's not clear whether we can scale this type of ELM, for example, SNN architecture, or LIF SNN or ALIF SNN architecture to, I don't know, GPT-4 performances. No one knows, but I think we need to think about how we can do this. And I believe there was a talk on Open Neuromorphic about essentially these neuroscience constraints not being constraints themselves, but actually we can leverage them. These are the advantage. The spiking is not a drawback, it's the advantage. Yeah, and I think, as I said, if we manage to find compact ways of computing locally and transferring sparse, highly informative messages, I think we're on long term on a winning road. Yeah.
That's some beautiful words for the end right there. Thanks a lot for that. I'm looking forward to some follow-up work of this. Are you going to continue to work on that in your
I hope.
next
Yes,
edition?
of course.
Nice.
I even did some preliminary SNN experiments, but it's going to take a while to really explore this.
Yes. No, that's okay.
And I'm looking forward to also, and this is the hope also for this presentation, to people use this model, tinker with it, improve upon it, and yeah, I'm looking forward to the experiments. Because essentially there is not much examples of models where you can just through a few hyperparameter changes really change how expressive it is, how long range. Like you can also artificially restrict how far it kind of can learn temporal dependencies. And I think there are so many interesting follow-up studies to be done with such an expressive neural model. I'm quite curious to see what people come up with, really.
Perfect. Thanks a lot for that. Yeah, this talk is available on YouTube for anyone who's watching on LinkedIn or Twitter. And yeah, thanks a lot, Aaron. And hopefully there's going to be another talk some point.
I'd be looking forward to it. Thank you very much for having me.
Thank you. Have a good night. Bye-bye.
Good night.